Let's check our understanding on integration being inverse process of differentiation. We know that integration is the inverse process of differentiation. So instead of differentiating a function, we are given the derivative of the function and asked to find its primitive, which is the original function. Such a process of obtaining an original function is called integration or anti-differentiation. Let us understand it with the help of the following example. We know that d over dx of sin x is equal to cos x. We observe that the function cos x is the derived function of sin x, where sin x is an antiderivative or an integral of cos x. Likewise, d over dx of x to the power of 4 upon 4 is equal to x cubed. Similarly, d over dx of e to the power of x is equal to e to the power of x. So, x to the power of 4 upon 4 and e to the power of x are the antiderivatives or integrals of x cubed and e to the power of x respectively. Therefore, we now have the derivatives of the functions sin x, x to the power of 4 upon 4 and e to the power of x. Again, we note that for any real number c treated as constant function, its derivative is 0. Hence, we can write these results as shown. Thus, antiderivatives or integrals of the above cited functions are not unique. Actually, there exist infinitely many antiderivatives of each of these functions which can be obtained by choosing c arbitrarily from the set of real numbers. For this reason, c is customarily referred to as arbitrary constant. In fact, c is the parameter by varying which one gets different antiderivatives or integrals of the given function. More generally, if there is a function f such that d over dx of f of x is equal to f of x, where x belongs to I or interval, then for any arbitrary real number c, also called constant of integration, d over dx of f of x plus c will be equal to f of x, where x belongs to I. Thus, f plus c, where c belongs to R, denotes a family of antiderivatives of f. Thus, we have a remark that we can make from what we learnt. Functions with the same derivatives differ by a constant. For example, let g and h be two functions having the same derivatives on an interval I. Consider the function f is equal to g minus h defined as shown. Then by hypothesis, we get f dash x is equal to 0, where x belongs to I as shown. In other words, the rate of change of f with respect to x is 0 on an interval I. Hence, f is a constant. Thus, we can conclude that the family f plus c, where c belongs to R, provides all possible antiderivatives of f. Well, the entire class of antiderivatives is represented with the help of a symbol as shown, which reads as indefinite integral or integral of f of x dx. Symbolical representation of integration of function f of x is as shown. Thus, the general notation for integration is as shown. For the ease our discussion on integration, it can be summarized as shown in the table. As of now, we are aware that integration is an inverse process of differentiation. Therefore, by using our prior knowledge of the formulae for the derivatives of many important functions, we can write down immediately the corresponding formulae for the integrals of these functions as listed in the table shown. These corresponding formulae for integrals are referred to as standard formulae, which will be used to find integrals of other functions. Remember that in practice, we normally do not mention the interval over which the various functions are defined. However, in any specific problem, one has to keep it in mind. So far, we have understood the integration of any function. But how do we interpret indefinite integral geometrically? Let's find out. Consider a function f of x equals to 2x. Then the integral of f of x dx is equal to x squared plus c. Note that for different values of c, we get different integrals. But these integrals are very similar geometrically. Thus, y is equal to x squared plus c, where c is arbitrary constant, which represents a family of integrals. As a result, by assigning different values to c, we get different members of the family. In fact, these different members together constitute the indefinite integral. In this case, each integral represents a parabola with its axis along y-axis as shown. So, for f of x equals to 2x, integral is equal to x squared plus c. Observe that for c equals to 0, curve is a parabola with its vertex on the origin. While we get the curve y is equal to x squared plus 1 for c is equal to 1. Note that we get a parabola shifted 1 unit along y-axis in positive direction as shown. However, for c equals to minus 1, we get a parabola shifted 1 unit along y-axis in the negative direction. Thus, for each positive value of c, each parabola of the family has its vertex on the positive side of the y-axis, and for negative values of c, each has its vertex along the negative side of the y-axis. Some of these have been shown in the figure. Let us consider the intersection of all these parabolas by a line x equals to a. In the figure, we have taken a is greater than 0. The same is true when a is less than 0. Note that when the line x is equal to a intersects the given parabolas at P0, P1, P2, P minus 1, P minus 2, and so on, respectively, then dy by dx at these points will be equal to 2a. This indicates that the tangents to the curves at these points are parallel. Thus, the integral of 2x dx is equal to x squared plus c, which is equal to fc of x. This implies that the tangents to all the curves y is equal to fc of x, where c belongs to R at the points of intersection of the curves by the line x is equal to a belongs to R are parallel. Further, the equation integral of f of x dx is equal to f of x plus c, which is equal to y. This represents a family of curves. The different values of c will correspond to different members of this family, and these members can be obtained by shifting any one of the curves parallel to itself. This is the geometrical interpretation of indefinite integral. Let's discuss and derive some properties of indefinite integral. We know that the process of differentiation and integration are inverses of each other. As a result, we get the first property, which states d over dx of integral of f of x dx is equal to f of x, and the integral of f dash of x dx is equal to f of x plus c. Let's prove this property. Consider an antiderivative capital F of function f of x such that d over dx of capital F of x is equal to f of x. Then the indefinite integral of the function f of x with respect to x is equal to capital F of x plus c. Further, take the derivative on both the sides, and on simplifying we get d over dx of integral of f of x is equal to f of x. Therefore, we have proved the property. Similarly, for f dash x equal to d over dx of f of x, the indefinite integral of f dash of x dx is equal to f of x plus c, where c is arbitrary constant called constant of integration. Well, the second property of indefinite integrals states that the two indefinite integrals with the same derivative lead to the same family of curves, and so they are equivalent. Let's prove this property. Let f and g be the two functions such that derivatives of their integrals are equal. Therefore, we get the equation as shown. As a result, we get integral of f of x dx equals to integral g of x dx plus c. Thus, we can say that the families of curves as shown are identical, where c, c1 and c2 belong to R. Hence, in this sense, indefinite integral of f of x dx and indefinite integral of g of x dx are equivalent. Hence, the second property is proved. Remember an important point, that the equivalence of the families as shown is customarily expressed as shown without mentioning the parameter. Now, as per the third property, the integral of f of x plus g of x dx is equal to the integral of f of x dx plus the integral of g of x dx. Let's prove this property. Consider left side of the property to be proved. then by using first property of indefinite integral, we can write the derivative of the integral of sum of the functions f of x and g of x dx is equal to the sum of the functions f of x and g of x. The right side of the property to be proved can be written as shown. Thus from 1 and 2, and by using property 2, we prove the required property. Here, let's state the fourth property, which states that for any real number k, the integral of k times f of x dx is equal to k times integral of f of x dx. Consider left side of the property to be proved. Then, by using first property of indefinite integral, we can write the derivative of the integral k times f of x dx equals to k times of f of x. Also, the right side of the property to be proved is equal to k times f of x as shown. Therefore, using the second property, we prove the required property. The fifth property of indefinite integral is actually derived from the third and fourth properties. Let's see how. Now consider the third and fourth properties of the indefinite integral as shown. In fact, when these properties are generalized to a finite number of functions, f1, f2, so on, till fn, and the real numbers k1, k2, so on, till kn, we get a fifth property as shown. Let's solve some problems. Write an antiderivative for each of the following functions using the method of inspection. Consider the first function. Now, we look for a function whose derivative is sine 2x. Note that the d over dx of cos 2x is equal to minus 2 sine 2x. Therefore, an antiderivative of sine 2x is equal to an antiderivative of sine 2x is minus 1 over 2 cos 2x as shown. Next, consider the second function 4x cubed plus 3x squared plus 2x. Further, we look for a function whose derivative is the given function. Note that d over dx of x to the power of 4 plus x cubed plus x squared is equal to the given function. Therefore, an antiderivative of the given function is x to the power of 4 plus x cubed plus x squared. At last, consider a third given function 1 over x, where x is not equal to 0. Now, we look for a function whose derivative is 1 over x. Recall that d over dx of log x is equal to 1 over x, where x is greater than 0. Therefore, d over dx of log minus x is equal to 1 over minus x into minus 1, which is equal to 1 over x, where x is less than 0. Combining the above equations, we get d by dx of log mod x is equal to 1 over x, where x is not equal to 0. Therefore, the integral of 1 over x dx is equal to log of mod x is one of the antiderivatives of 1 over x. Find the given integrals. Let us consider the first integral, which is equal to the integral of x dx minus the integral of x to the power of minus 2 dx. Now we find the respective integrals as shown. Thus we get the required integral equals to x squared over 2 minus 1 over x plus c. Now consider second integral, which is equal to the integral of x to the power of 5 by 4 dx minus integral of 1 dx. Next, we find the respective integrals as shown. Thus we get the required integral equals to 4 by 9x to the power of 9 by 4 minus x plus c. Here is now the third integral as shown. The given integral is equal to the integral of x to the power 5 by 3 dx plus the integral of 5e to the power of x dx minus the integral of 4 over x dx. Further, we find the respective integrals. Thus we get the required integral as shown. Find the following integrals. Now let's consider the first integral. The given integral is in fact equal to the integral of cos x dx plus integral of sin x dx. Thus we get the required integral as sin x minus cos x plus c. Next, consider the second given integral. Note that it can be written as integral of cosec squared x dx plus integral of cosec x into cot x dx. Further evaluating respective integrals, we get the required answer as shown. Let's now consider third given integral. Note that it can be written as integral of 1 over cos squared x dx minus integral of sin x over cos squared x dx. Further, simplify and find the respective integral as shown. Thus we get the required integral as tan x minus sec x plus c. Find the antiderivative f of f defined as shown. One antiderivative of the given function f of x is x to the power of 4 plus 2x because its d over dx is equal to 4x cubed plus 2. Therefore, the antiderivative f is given by f of x equals to x to the power of 4 plus 2x plus c. We are given that f of 0 is equal to 5. So substitute x equals to 0 in f of x as shown and then get the value of c equals to 5. Hence, the required antiderivative is the unique function f defined by f of x is equal to x to the power of 4 plus 2x plus 5. Well, now let's compare differentiation and integration. We know that differentiation helps us to find a rate of change of one quantity compared to another. And since the integration is the reverse of differentiation, like we may be given a rate of change and we need to work backwards to find the original relationship between the two quantities. Both differentiation and integration are operations on functions. Further, both satisfy the property of linearity as shown. As we have already seen that all functions are not differentiable. Likewise, all functions cannot be integrable. We will learn more about non-differentiable functions and non-integrable functions in higher classes. Next, we know that the derivative of a function, when it exists, is a unique function, while it is not true for the integral of a function. In fact, they are unique up to an additive constant, that is, any two integrals of a function differ by a constant. Therefore, the integral of f dash of x dx is equal to f of x plus c. Now, when a polynomial function p is differentiated, the result is a polynomial whose degree is 1 less than the degree of p. However, when a polynomial function p is integrated, the result is a polynomial whose degree is 1 more than that of p. Moreover, we can speak of the derivative at a point, but we never speak of the integral at a point. In fact, we speak of the integral of a function over an interval on which the integral is defined, as will be seen later. Next, the derivative of a function has a geometrical meaning, namely the slope of the tangent to the corresponding curve at a point. Similarly, the indefinite integral of a function represents geometrically a family of curves placed parallel to each other, having parallel tangents at the point of intersection of the curves of the family, with the lines orthogonal, perpendicular, to the axis representing the variable of integration. What is more is that the derivative is used for finding some physical quantities like the velocity of a moving particle when the distance traversed at any time t is known. Similarly, the integral is used in calculating the distance traversed when the velocity at time t is known. Also, differentiation is a process involving limits. And so integration too involves limits, as will be seen later. At last, we state that the process of differentiation and integration are inverses of each other, as we have discussed earlier.